Welcome to Shanti-Peace for Mathematics. In this video, we are going to discuss about how to find out the complementary function for ordinary differential equation. So before doing that, let us write down what will be the general form of nth order linear differential equation. So the general form of nth order linear differential equation can be written as Pn of x into dn y upon dxn, that is the nth order derivative of y with respect to x, plus Pn minus 1x into n minus 1 the derivative of y with respect to x up to so on p1 x y plus p0 of x is equal to 0, where this pn minus 1, p1 and p0 are the functions of x only. So I can say pn are functions of x only for any n running from 0, 1, 2 up to so on. If this p0 is 0, then the equation is known as homogeneous equation. So I can say that if p0 of x is equal to 0, then equation 1, this is the equation 1 I can call, it's called homogeneous ODE, ordinary differential. And if p of 0 is non-zero, then that equation is called the non-homogeneous ordinary differential equation. The general form of linear differential equation with the constant coefficient, that is our objective, is to solve, to write down the complementary function for such differential equation, which is of the form d power n y by dx power n plus a1 d power n minus 1 y dx power n minus 1 a2 d power n minus 2 y upon dx raised to n minus 2 up to so on a n y equal to some other function, let's say r of x. In the previously, what we have here, this pn minus 1, p1 and p0, here they are the constant functions. So that the constants we have written here in this manner. If r of x is 0, then it's called the homogeneous differential equation. That is again the same thing that we have. Now our main objective is to find out what is the method to write down the complementary function for the ordinary differential equation with the constant coefficient. So for that we have a steps. So let us have the first step. The first step is to write down the differential equation in terms of d. So it is in terms of a symbol d. So that symbol d is represented in this manner. D by dx we call it as capital D. D square y by dx square we call it as capital D square, and so on. D power n upon dx power n we call it this is as d power n. This is the step 1. In the step 2, we'll write this equation into the form, into the d form. So that means the first quantity that we have here, that is a d power n. So we can write down this is d power n y plus a1 d power n minus 1 y plus a2 d power n minus 2 y up to so on dy plus an y, this is a n minus 1 is already there, equal to r of x. Now since this is an operator, d by dx is an operator, d square y by dx square is also an operator, so this quantity I may rewrite as d power n plus a1 d power n minus 1 plus a2 d power n minus 2 up to an minus 1 d plus an y equal to r of x, and we call it, this is the quantity as p of d, that is the polynomial, or I can say it is a polynomial function in d. So we can write down that is as p of dy is equal to r of x, where you can say that P of D, which is the D power n, plus A1 D power n minus 1, A2 D power n minus 2, up to so on, An. So in this manner, your P of D we have assumed and we can write down as a function. So it is a polynomial function into the D. And now we can write down the auxiliary equation. So the step 3 is to find out the solution for the auxiliary equation. What is the auxiliary equation? The auxiliary equation we can write down is P of D equal to 0. This is the auxiliary equation, and since this is a polynomial function, will be the polynomial, and by fundamental theorem of algebra, because its degree is n, so it has n roots in a complex plane. So that's why we can factorize that into this form. So may I write down this is d minus m1, d minus m2, up to so on d minus m2 equal to 0. That are the roots of this polynomial. So we can say that m1, m2 up to mn are the roots of this polynomial. That is the step 3 to factorize this polynomial. The step 4 is very important, and for that I am making as a table here. Since this is the roots of the polynomials m1, m2, m2 up to mn, the complementary function depends on how these roots are behaved. So let us write down what is the rules for that. So I am just writing the roots. The first one is if all roots are real and distinct, that means they are different. If they are real roots and all of them are different roots, then you can write down the complementary function. In short, people can write down this is a CF, complementary function, and it is denoted by YG. That we can write down. So let's say this all roots are real and distinct, and say that roots are m1, m2 up to mn. So the complementary function can be written as C1 e power m1x plus C2 e power m2x up to so on Cn e power mnx. The rule number 2, if all roots are real but two roots are repeated, that means all the roots are real but among them two roots are repeated, that means m1 is equal to m2 and then other roots are m3, m4 up to so on. That is the form of these roots are there. Then the complementary function you can write down as C1 plus C2x e power m1x up to so on c power mnx. Step or rule number 3 is says that let's say instead of two roots, let's say three roots are repeated. For example, all roots are real and m1 is equal to m2 equal to m3. Three roots are equal and the m4 m up to mn are the different roots. Then the complementary function can be written in the form of c1 plus c2x plus c3x square e power m1x up to Cn e power mn. The rule number 4 that we can say, a pair of complex roots is there. Because it is a solution for the polynomial, it may happen that roots are complex number. So I am saying that pair of complex roots and all other are real. So if the pair of complex roots are there, let's say m1 equal to alpha plus I beta, and that is the rule for the polynomial that if the one complex root is there, then the other complex root will be the conjugate of the same. So that's why the another roots will be m2, which is alpha minus I beta, and m3, m4 up to so on mn are other roots as it is. Then in that case, the roots can be written as, or the complementary function can be written as e power alpha x c1 cos beta x plus c2 sin beta x plus c3 e power m3x up to so on cn e power mnx will stay as it is. The next and the last one is that if the two equal pair of complex roots is there and all other roots are real. In that case, you will have the equation which we can write as m1 is equal to m2 is equal to alpha plus I beta. So that is the two pair of complex roots are same, and m3 m4 is alpha minus I beta, that we can denote, and m5 m6 up to so on mn are all real roots we have. So in that case, you will have the solution can be written in the form of e power alpha x c1 plus c2x cos beta x plus c3 plus c4x sin beta x plus c5 e power m5x up to so on cn e power mnx. So these are the way you can write down the complementary function for any differential equation. Okay, so let us revise what is the steps we have did. The step 1 is to write down your in the notation of the D. The step 2 is convert your given differential equation into the operator form D. The next step is to solve the polynomial equation, its auxiliary equation, that is the solution or finding the roots of that equation, and based on that roots we can able to write down the complementary function. So if the two roots are real and different, all roots are real and distinct, then we can write down solution in this manner. If the two roots are equal, then we can write down in this manner. If three roots are equal, then we can write down in this manner. Now you know the pattern. If the four roots are same, then you are able to write down what is the solution for complementary function, or how we can write down the complementary function. The next is if pair of two complex roots are there, then we can write down in this form. If the two pair of complex roots are there, then we can write down in this form. So in that way you can get the idea now. Now what is the rule is behind this whole process? That is one theorem. It says that if any differential equation is of nth order, then it has n linearly independent solutions. And this whole process to write down the complementary function is based on the linearly independent thing. Then how we can say that two functions are linearly independent? For that also I will make one of the video and show it to you how we can say that the two functions are linearly independent. Now let us find the solution for the differential equation and let us solve some examples regarding this complementary functions. The first example that I am taking is d square y by dx square plus y equal to 0. So if I write down d by dx as d and d square by dx square is equal to this square, this equation can be written as d square plus 1 y equal to 0. So therefore the auxiliary equation that I can write down in the short form ai is d square plus 1 equal to 0. That d square plus 1 is equal to 0 will gives you two roots. So I can say it is d square is equal to minus 1, which I can write down I square. So that means that d equal to plus or minus I. So it says that this equation has two roots. One of them is I, another one is minus I, and they are the complex roots. So therefore the solution, or we can say that the complementary function that we can write down in the short form CF is as per the rule. What will be the rule is e power alpha x cos beta x plus c1 cos beta x plus c2 sin beta x. So you can say that here alpha will be 0 and beta is 1 because it is of the form alpha plus I beta. So if you compare real and imaginary part, you will have this is the things. So therefore the solution is e power 0x c1 cos x plus c2 sin x. So that we can write them as c1 cos x plus c2 sin x. That is the solution for the differential equation. For this, let's have the next example. Let us take this equation d cube y by d x cube plus y equal to 0. So if you can write down this is into d form, so we can write down this is d cube plus 1 y equal to 0. Therefore, the auxiliary equation we can write down as b cube plus 1 equal to 0. That will implies this b cube, that we can factorize as a cube plus b cube, that is a plus b a square minus ab plus b square. Due to this, we can write out this is a d plus 1 into d square minus d plus 1 equal to 0. So therefore, this will gives you d equal to minus 1, and d will be the solution for this. Another roots are 1 by 2 plus or minus I root 3 by 2, that you can verify by yourself, and hence there is one real roots and 2 are the complex roots. So therefore, the complementary function we can write down, or I can say a solution for this differential equation we can write down as y equal to c1 e power minus x, that is m1x, that is minus 1, plus e power 1 by 2x, that is alpha, 1 by 2 is alpha, beta is root 3 by 2, so it is c1 cos beta x, that is root 3 by 2x, plus c2 sine root 3 by 2x. So that is the solution for this differential equation. Let's have the next example. D power 4y dx power 4 plus y equal to 0. If you can write down this is into the d form, then we can write down this is d power 4 plus 1 y equal to 0. The auxiliary equation that we can write down is d power 4 plus 1 equal to 0. This we can factorize into the different manner. So we can say that d power 4 minus 2d plus 1 2d square. So I am adding 2d square and subtracting 2d square here. And since I am adding this 2d square here, this will be d plus d square plus 1 whole square minus root 2d whole square equal to 0. So that's why we can factorize this as d square plus 1 minus root 2d and d square plus 1 plus root 2d equal to 0. And since so therefore this has a two factor, that is d square minus root 2d plus 1 equal to 0, or d square plus root 2d plus 1 equal to 0. Since this is a quadratic equation, so it has a two roots. What are the two roots is? Let us write down that. That is 1 by root 2 plus or minus I 1 by root 2, and this will have minus 1 by root 2 plus or minus I 1 by root 2. So it is a pair of two complex roots are there. So we can write down the solution in the form as, so the y, which will be the complementary function here, it will be the solution, which is e power x by root 2 c1 cos x by root 2 plus c2 sine x by root 2. That is for the first root, that is the first root is this 1 by root 2, 1 by root 2. Another root is minus 1 by root 2. So for that we can write down solution as e power, so plus e power minus x by root 2 c1 cos x by root 2 plus c2 sine x by root 2. So that is the roots of this complex. So that is a complementary function for this equation. Here in that manner you have already done a lots of example for calculating the complementary function in your BSc class. So in this video we have discussed how to calculate the complementary function for homogeneous differential equation and how to write down the solution for the same. Thank you very much for listening me. If you have liked this video, please press the like button. If you have any comment, suggestion or question, please drop down in a comment box below. See you in next video. Till then, bye bye, sayonara.